Hey guys, Greaves here, back. We're going to look at today's little lesson, sound and the Doppler effect, okay? So what I mean by sound is obviously sound waves, right? So let's take a look, right? First of all, sound, what is it, right? Well, it is a longitudinal wave, right? Well, we went over this last week, or last couple of videos, I should say, right? And it's difficult to represent a longitudinal wave, right? So let's look at a slinky, right? So here's a slinky, right? And I can like squinch it together, right? So here's a slinky, right? Right? So I hope you can see this here, right? So these areas in the slinky, it's spread apart. Here the area, here the area, and here the area. The slinky are kind of compressed together, right? So really what happens is as energy, right, is moving, let's say in this particular case left to right, the particles in the wave are wiggling back and forth, right, parallel to energy transfer. So that's really what a sound wave is. It's a longitudinal wave. Really what it is. Think a little molecule of air. There it is. Here's another little molecule of air, a little molecule of air, etc., right? So when we speak, right, what I'm really doing is I'm kind of pushing this molecule to the right, air molecule that is. It's going to hit into or bump into the molecule next to it, right? When it bumps into it, it's going to give its energy. This guy's going to snap back. This guy's going to go here, right? And so forth and so on. So here is a longitudinal wave, okay? A couple of things about a sound wave, right? Velocity of sound wave, right? In air, it's about 330 meters per second at STP, right? This is on the reference table. It's not really something you need to worry about, right? We're saying just, hey, a typical situation, sound travels about 330 meters per second, right? So if that's said, we're going to use velocity is equal to frequency times wavelength, and we might be able to find some information. I'm not going to get too crazy with this now, okay? All right, so, maybe I'll give you some problems on test result or something, but we'll just see how that goes, okay? So let's take a look at something, just to give you something in perspective, all right? Let's give something in perspective. Let's talk about human hearing, right? Right? Human hearing, do we have good hearing, poor hearing? Well, let's see. We can hear about something that has about 20 hertz to about 20,000 hertz. Now, believe it or not, I would spend like 10, 15 minutes in class. I have really some good stuff with this. I can't do it here, right? Right. So what does that mean? Well, look, this is the range of human hearing. What does that mean? Well, we can hear sound, right? Waves, I should say, sound waves that are really in this range. So what does that mean? Well, here is a sound wave. Should say here's a particle of air, right? What does it do? Well, it's going to wiggle back and forth, right? Remember what frequency is. Frequency is the number of cycles per second. So if I can get a sound wave to move back and forth about 20 times per second, right, I can hear that. Obviously, if I take it up to 40, 50, 100, etc., the faster that it wiggles, right, I can hear that as well. However, there is a limit to our hearing, right? Once we get to that 20,000 range, we're no good anymore, okay? And believe it or not, most people are a little bit below. You guys being pretty young, we would do it in class. You guys could read hear about 17, 18, 19,000. I can't hear it anymore, right? So that's our range of hearing, okay? To put that in perspective, how about your dog or cat, right? Probably a pet that you have at home. Well, they're good at that same low range. However, they can go up to 50,000 hertz. What does that mean? Once that sound wave wiggles back and forth, 22, 23, 24, we can't hear it. However, you guys all know that dog whistle that you've probably seen. You blow that dog whistle, you can't hear it at all, but your pet dog comes running, right? Because their range of hearing is much, much better than ours. Well, I like to just say this, right? It's kind of interesting. What is one of the best animals here that has range of hearing? Well, believe it or not, the bats, right? They have very, very good hearing. They go from about 20 hertz to about 100,000 hertz. Well, why is that good for them? Well, first of all, they use their hearing, right, to hunt, right? They send out these clicks, really sonar waves, right? And they're sending out very high frequency waves, and it's, believe it or not, they're tuned to like hear the echo back. And when they hear that echo with their ears, and they can triangulate it, and they can actually find little insects in the air, right? So pretty cool stuff, right, for those guys, right? All right, so that's just to put things in perspective, right, of hearing and what we can hear and what an animal hears and etc., right? All right, let's take a look at something, right? Another characteristic of sound, loudness. Okay, and this, by the way, is important, right? Because we're in what's called mechanical waves. Well, how do we represent loudness? Well, that is going to be the amplitude of the wave. Now, this is not a sound wave, but I'm going to draw this wave right here, right? So this is going to be a transverse wave, right? So this transverse wave, what would be the amplitude? Well, that's the amplitude of this guy. I'm going to take blue and let's make a wave that looks like this. All right. Well, look, here are two different waves, blue and black, right? There's the amplitude of the blue wave. What's the difference between the two? Well, believe it or not, they have the same, roughly the same frequency, right? Because they're completing the same amount of cycles per second, or in the same wavelength, I should say, right? But they have different amplitudes. So, right, the amplitude of these waves are different, which means if these were sound waves, which they're not, right? These would represent the difference in loudness, right? Which really, in this particular case, is my energy, right? Just to let you know, energy of these waves are directly related also to amplitude, right? So these are the mechanical waves that we've been talking about, okay? So let's continue. Ready? Okay, let's give you an example of something that I want to talk about. Example, right? Let's look at frequency, right, and pitch. All right. Should have said this before, I think, but we'll take care of it now. All right. So we hear, right? We hear the That's not the right word. Our ears, our senses are in tuned to the frequency of a wave. Believe it or not, inside your ear is an eardrum, right? That eardrum is going to wiggle back and forth, right? The faster that it wiggles, right, the higher the frequency. We mentioned before that if it's going back and forth more than 20,000, can't hear it, right? It's just out of our range of hearing, right? So, but we perceive frequency and our brain translates that to pitch, right? So let's take a look at something. Let's take a look at this wave here. So here's a wave. By the way, I really want to talk about sound waves, right? But it's really, really hard to draw a sound wave. So I always draw them as if they're transverse, but they're not transverse, they're longitudinal, okay? It's just easy to get the point across if I'm drawing a transverse wave, right? So let's see, here is wave A, here's wave B. Right? So there are two waves, right? All right, well, what's the difference between the two? Well, this guy right here is going to be low frequency. This guy here, right, is going to be what we call high frequency. Well, why is this low frequency? Why is this high frequency? Well, obviously, I'm stuffing more waves, right, in a bigger, same distance, right? All right, well, how would our brain perceive this? This low frequency is what our brain translates to low pitch, right? This high frequency is what we translate to high pitch, okay? All right, so this is how frequency and pitch are related. It's going to come up in a minute that we need to kind of be aware of this stuff, okay? All right, so what about amplitude, right? So how do I represent amplitude? All right, so once again, I'm drawing, right? Transverse waves, but I really want to talk about sound waves, which are longitudinal. It's just difficult to draw them, right? So there I have two waves, right? Amplitude. Well, what do I have? Well, I would say this is what? A big amplitude, which means this, we perceive this as loud, or it has a what? A lot of energy, right? This guy right here is a low amplitude, right? Which we would say is a soft, right? And, well, not a lot of energy, right? So there is kind of how we look at amplitude of a wave. It's loudness, and it's also energy, okay? I'm going to link to you guys a video on YouTube. I'd like you to stop my video now, and I want you to go to that. I want to take a look at that real quick, okay? And then come back, obviously, to me. All right, so now we're back, right? And I want to take a look at the Doppler effect. Now, you saw a little video on the Doppler effect. Well, what is the Doppler effect? Well, it is the apparent shift in frequency due to the relative, right, motion of source and receiver. E-I-V-E-R, right? Not sure how to spell that. Receiver. I think it's receive. Well, you get the point. Receiver, okay? All right, so now I want to take a look at how the best way to kind of visualize this. Okay, so look, how do I represent a wave? Here's a transverse wave, right? There it is, okay? Let's say this is the water wave. Here's my map of my ball again. There it is, right? And we are looking, right, down at the water wave. Now, what does the person see? There goes the water wave zipping by. Now, these are the crests, right? So there's crest 1, there's crest 2, right? Here's crest 3, etc. Now, we should recognize that the distance between consecutive crests is going to be a wavelength. Troughs as well, right? So, if I want to represent the Doppler effect, we look at this from a different point of view. Let's peek downward at a lake and drop like a pebble into the lake. So there is the pebble. I'm dropping it into water. Well, what happens to the water? Well, everyone recognizes that the water waves are going to ripple, right, outward from the center, right? So what do these solid lines represent? Well, the solid lines are going to represent the distance between crest to crest, crest to crest, which means that this distance here is a wavelength. That's a wavelength. That's a wavelength. That's a wavelength. That's a wavelength. And that's a wavelength. Okay? Now, let's take a look at the Doppler effect. What did I say the Doppler effect was? It's the apparent shift in frequency due to the relative motion of the source and the receiver, right? So let's let this, whatever this object is, to be at rest, right? Let's put person A here, and let's put person B there, right? And let's make this a motorcycle, an engine, right? What's happening? As the engine's revving, sound waves are going to the right and to the left, right? And what that means is sound waves are going to pass person A and person B. Well, how is this person going to perceive the sound waves? Well, we're going to get a frequency and a pitch. This guy's also going to get a frequency and a what? Pitch. TCH, right? So compare frequency and pitch from A to B. Well, this guy's same as B. This guy here is what? Same as A, right? All right, so now let's take a look at what happens with the Doppler effect. The Doppler effect is I'm going to get an apparent shift, right? By the way, I'll talk about it later, but really, once the source produces a wave, the frequency never changes. However, we might be able to perceive these things differently. All right, so let's take a motorcycle and let's zip the motorcycle very fast to the right. So we're going to say this guy has some non-zero velocity to the right. And what happens? As he's moving to the right, the front of the waves are going to start to get squished together. Okay? I'm going to exaggerate them. Right? So this object is moving very fast to the right. So here now is A. Here now is B. Okay. So let's see what happened. Stationary. The wavelengths on the right side and the left side are exactly the same distance. So this person and this person are hearing the same exact frequency and pitch. But look what happened. As I start to move this object to the right, the wavelengths in the front start to get squished together. So if the wavelengths get shorter, velocity is equal to frequency times wavelength. As the wavelengths gets what? Shorter, the frequency must get bigger. So the person over here, here's a frequency is high, which means the pitch is going to be high. How about this person over here? This person here, frequency. Well, look what happened to the wavelengths. They got bigger. So low frequency means the pitch here is what? Going to be low. Okay? So this is an example of the Doppler effect. Everyone here has experienced this. When that motorcycle has come zipping towards you, right? The engine is really high, and it goes past you, it gets really low. Okay? So this is kind of the Doppler effect. I'm going to try to get another little applet for you. If I can find one, I'll include it on this with you, and I'll let you take a look and mess around with that. All right? So this was a little more info on waves and the Doppler effect. All right? See you later, guys.